Today we are, you don't have to use your calculator, okay? I think I mentioned this maybe in Friday's lecture. But we're still on track. Tomorrow in lab, you're going to be using Bunsen burners. I think I mentioned that before, so tie your hair back or live dangerously. And also tomorrow, no, not tomorrow, a week from tomorrow is your second unit exam. So on Friday, I'll bring like an outline kind of what you're going to run into on your Unit 2 exam. So we're all on the same page that way. So today you don't need a calculator, and we're going to be talking about electrons. So we went around the room the other day, and you guys told me kind of how an atom works. You guys said that this is the nucleus, and you guys told me we have protons and neutrons in the nucleus, and we have electrons outside the nucleus. Okay. I heard an analogy of kind of, we did the BB in the 10-story building, but if you make the nucleus the size of a blueberry, okay, and if you put it in, I don't know how many people the stadium seats, but if you put it in a large, like, athletic stadium, the blueberry to scale is the size of the nucleus, and then out to the edges of the stadium would be where the first electrons are. That's kind of cool. So this actually, you don't have this slide here, but this is a review slide. I think this is amazing that, we just take atoms for granted. They're so overlooked these days.
Unit 2, Part 4?
What's that? This is. Yeah. Oh, yeah.
I'm pretty sure we have that slide. Yeah, we do.
Oh, you do. So this is part 4. Thank you. You do have that slide. Thanks.
You're welcome. I was just going to put the wrong spot.
But we did look at this before, kind of from the red one to the green one. That's what we know about an atom. Did you guys hear, like, the Nobel Prize in science went to a couple of chemists recently? Yeah, I'm just saying. What'd they do? They used, it's like mini machines. So to me, it's almost like biochemistry or biology. Things that can actually be injected in a person can act as machines. But this is not so unusual to what biologists have known for some time, that biomolecule will react differently with different stimuli. So anyway, that's kind of cool. But I want to focus on these guys down here, okay? These guys down here. So Bohr actually, these little yellow orbs are electrons. And what Bohr said is that electrons are kind of organized into certain energy levels. And what Schrodinger went on and said is that kind of gave shape to where the electrons are. That's the way I think of it. So here we go. This is our first look. That black thing right there, that's the nucleus with the protons and the neutrons tucked away. That's our blueberry. And then you can see like the lines, and those lines are where an electron can hang out at different, what we say, energy levels. Now let's see, how does this work? Literally, this is, as they're drawn up, this is the lowest. And I'll put a big E for energy. That's the lowest energy. And n is equal to 5, that's the highest energy. Now these n's actually, these are big old honking energy levels. And as we kind of go about our business, we're going to see that those big old honking energy levels are actually subdivided in sub-levels. Okay? So that's kind of how that goes. So Schrodinger, which was the green one, okay, Schrodinger said, yes, electrons reside at certain energy levels, but he gave more, like I'd say, shape to where electrons are hanging out. Now, where electrons are hanging out, we call electron orbitals. Okay, orbitals. Orbital is a region of space around the nucleus where electrons are hanging out. So orbital not only gives it space, but orbital also gives it how much energy does that electron have since it's there. So I think it's both of it. Okay. So you kind of saw with the little black nucleus and kind of the n is equal to 1, n is equal to 2, n is equal to 3, think of it this way. Electrons can't be in between. There's no 1.5, okay? There's no 2.5. They have to be at 1, or they have to be at 2, or they have to be at n is equal to 3. Now again, there are kind of subshells in those those ends are what we call principal energy levels. So in that sense, it's what we say quantized, okay? And that has some awesome consequences in everyday life. That electron, the energy associated with electron is quantized. So a quantized value, and I'm going to give you an example of another quantized value here in a minute, but electron's energy has to be quantized. You can't hover between two. So here we have two chemists, chemist on the left, chemist on the right. They look there like they're at similar elevations, similar levels, okay? So the deal, though, with the guy on the right is those are awfully big stairs, first off. You know, it's like hip high. I'm like, dude, climb those stairs. Especially with the beaker like this. But that's not the point. The point is he can be here, he can be here, or he can be here, but he can't hover. So that's more like how electrons are, okay, with regard to their energy. Okay, electrons can be here, here. This would be more of a continuum, okay, and this is quantized. So.
Do we have a box to fill in the previous slide?
Yeah. If we go down.
This one?
Yeah, we have to write all
You have to write all that down? Okay. Hand cramp. Okay, so a quantized value is one that can exist in only one of several states, but not in between. No 1.5 Z's, 1 3/4 Z's. It's 1, 2, 3. Like kind of a whole number integer approach. It's funny how sometimes my slides you get to fill in a hole. A lot of words, and sometimes it's just a word here and there. Oh, while I'm thinking of it, and so thanks for telling me to make sure that we went back to this slide. Your Unit 2 exam is going to have a vocabulary section, and that's a wonderful word to put in my vocabulary section. So there's all sorts of words. If you're preparing for your unit exam, you probably know this, you're going to want to go through your notes and pull out key terms. Just love those electrons. It feels like Monday.
I think it's because it's rainy outside.
That could be.
It's like dark.
It is.
I'm always tired when it's like dark outside.
Yeah. Makes us appreciate when it's sunny, I guess. So we did this one. Very good. So we kind of have, again, the quantized elevation. And not only that, but there's these things called energy diagrams. And all it is a plot. Okay? So along this would be the y-axis, we actually put energy. Okay, so we're going up in energy as we go to from n is equal to 1, n is equal to 2, okay? So actually, those cute little electrons that are clear out there at n is equal to 6, they literally have more energy than the ones on n is equal to 1. Okay. So, if I were to ask you how many electrons does a hydrogen atom have, how many electrons does a hydrogen atom have? Just one. It's unique in that way, because then everybody else is what we have, multi-electrons. Okay. So actually Bohr studied hydrogen a lot. And he found that hydrogen, that one electron around hydrogen, he found it here. Now here's the deal. If he added energy, he found that one electron could go up to n is equal to 2. If he added even more energy, it could go up to n is equal to 3. And do you buy this, that since its jump is quantized, since it has to, that is a certain amount of jump, then the energy put in is also quantized. So that's to say, it only sucked up just the right amount of energy to go up to the next energy level. And the cool thing is do you buy this, that when it went down, what do you think it did with energy? As it goes down, what happens to that energy? It actually gets less and less. And it actually releases little packets of energy as it does that. It happens all the time. Okay, so I call them couch potato electrons, as they're all at the lowest energy they can be. We say those electrons are at their ground state. Now, we're going to see that, like, and I'm going to end up drawing kind of a, I call it the onion, but I'm going to draw a diagram over here. We're going to see that there are certain rules. So n is equal to 1, n is equal to 2. So these are what we call principal energy levels. Let's see, do I have enough room? Okay, and I said we're going up in energy. But we're going to see that actually there's only so many electrons that can be here, so many electrons that can be here. Okay, they run out of room. Oh, you guys needed this, didn't you? Sorry. So I'm going to go ahead and draw a little mark here for, I'll draw a box here. And that's where, that actually is going to be my orbital. I'll put E, so E minus for an electron, orbital. Okay, and here we go. I'm going to go ahead and put in an arrow, and anytime you see an arrow, that is 1 electron. 1 arrow equals 1 electron, 2 arrows equals 2 electrons, 3 arrows equals 3 electrons. Okay, so these electron orbitals, these were the things that Schrodinger came up with. Okay, so that is where a ground state electron around a hydrogen nucleus is. Oops, sorry. So what Bohr found out is that we can zap that electron with energy. I'll put energy, then E for energy in, and it can be promoted to, it can skip up to the next energy level. That is what we call an excited state of that electron. Goodness, excited. Okay? That's just all that is. But like this slide says, it doesn't want to stay there for long. It won't stay there forever because it wants to go back and watch TV, be a couch potato. So electron orbitals, like I said, like we saw earlier, are two things. They are physical regions of space about the nucleus where electron is hanging out. Okay? And the other thing electron orbitals do is have an energy associated with them. So they kind of serve two purposes. And somewhere in there, so today I just want to kind of talk about where electrons can be, and then Friday's lecture will be important because we'll actually kind of organize electrons more. Where is my little? But one of the things you might want to start thinking about.
It's on the board.
Is it on? Oh, you are good.
I heard it all.
Thank you. Oh, okay. So anytime I draw a box, that's an orbital. Okay, box is an orbital. Perfect. Okay. So electrons are hanging out in orbitals. So, and by the way, electrons are arrows. Electrons are, when we draw them kind of like this, are represented by an arrow. That is an electron hanging out in an orbital. Okay, so I think chemists or scientists are good about wanting pictures instead of words, so I think that kind of does it. So one rule, and actually it's Hund's rule coming up later, but you see what this says is if you have one orbital, one box, you can only have 2 electrons. So the other important little tidbit is that if you do have 2 electrons, I'm going to draw another arrow there, but they have to have opposite spins. And we don't get into that much in intro Gen Chem. But I'm going to show the opposite spin by just showing the arrow pointed down. Okay, so that's it. There I have applied the whole opposite spin thing. So here we go. Here's my orbital. There's my 1 electron. I'm going to add another electron. He's going to have a roommate. And he is going to have the opposite spin. How do I show that with a picture? I show the arrow going the other way. All right. So now this is where we can take these, what we say, principal energy levels, these main energy levels, and we can break them out into subshells. There are 4 types of subshells we need to worry about. And they are, if you want to do S, P, D, and F here, you can. Those are subshell types. These are subshell types. All right. What else we got? This one, where it's called energy levels, that actually is our N, equals the N. The N I have up here, N is equal to 1, N is equal to 2, N is equal to 3. Those are what we call your principal energy levels. All right, so far so good. The whole subshell thing, it's easier to show you than to explain it, I think. Okay. Oh, let's see. Well, I have a slide coming up. Let me go ahead and just do it over here. What did I tell you? I told you S. I told you P, D, and F. Okay. I'm going to draw a box here. What's this box? It is an orbital. It's hot in here, isn't it? Just me. Okay, good. Okay. Now, S-type subshells can only have 1 orbital. P-type subshells have 3 orbitals. Okay? And then it's all about the oddsies, not the evensies. So how many orbitals do you think a D-type will have? Increases by 2, 5. And I apologize for my boxes, they get really sloppy. And then 7 for the F. Okay, so these are subshell types. Those are subshell types. All right. So all this is saying is that if you have, let's pick on D, if you have a set of orbitals, I think this is kind of fun, that are all in the same principal energy level, the same subshell, okay, those 5 orbitals are degenerate. They're equal in energy. That's all it says. See, to me, in order for this to make sense, you had to kind of know that. So. All right. What did this say? This said degenerate orbitals. Okay, this kind of says a similar thing. A subshell of orbitals, now you kind of know what a subshell of orbitals looks like. A picture person, subshell of orbitals. If it's an S-type, it only has 1 orbital. But otherwise, you have 3, 5, or 7, okay? They are degenerate, which sounds like a bad thing, but actually it's a good thing. All right. So here's a figure from your textbook that basically does what I did over here. You see the S? Okay, well, actually it doesn't do what I did over here. Now, let's take that, and I'm going to add it right here. So when N is equal to 1, what your slide says is you have 1 blue, you only have 1 S-type. I'm going to go ahead and go out on a limb, and I'm going to call this energy 1S. I'm going to put 1 box. Now, when N is equal to 2, they said you have an S and now you pick up a P. So I'm going to go N is equal to 2. I'm going to go 2S, one box, and I'm going to go 2P. Notice how I went to put the 2P above the 2S. Little higher energy. I'll put 3 boxes. Does that work? When N is equal to 3, looks like I get to pick up my first D. Now I have a 3S, I have a 3P, and I have now a 3D. Is that right? Now, on Friday, we'll kind of clean this up a little bit, but just for kicks, I'm going to go ahead and put on kind of this diagram that N is equal to 4. We get to pick up that last type of subshell. So we have the 4S, and we have the 4P, and we have the 4D, excuse me. And we now have the F-type subshell, the first F-type subshell. Is there a 3F? No. Is there a 2F? No. That's kind of how that works. 7, 5, 6, 7. Okay? That's it. So I'll just kind of give you a precursor of what we're going to be doing. So for instance, we pick on a carbon a lot. Carbon's atomic number 6. It has 6 protons. If it's neutral, it has 6 electrons. And this is how we use this sort of diagram. So 6 electrons, right? So this is where the first 2 are going to go. This is where the second 2 are going to go. That's 4. And we'll talk about this on Friday. So I need 2 more. Wait, 4, yeah, 5, 6. And actually, it's called actually, this is called Hund's rule. The other one's Pauli's exclusion principle. Do you see where, and I know this is kind of small, but do you see where I gave them separate rooms? Okay. 6 electrons, 1, 2, 3, 4, 5, 6. Okay. As I've drawn this right here, I have 6 electrons. I have kind of shown how they're hanging out. That's exactly how the electrons around a carbon atom are hanging out. Okay. That's it. Totally it. So we're only going to worry about the subshell types S, P, D, and F, but there are G, H, and I. Okay. Now, as we talk on Friday, when we start to see how electrons are hanging out around atoms, you'll see that we don't use G, H, or I as long as their set of electrons are in what we call their ground state, their lowest allowed energy for that set to go. But you already see that we have some rules with regard to where electrons can hang out. Okay. So let's kind of finish up here. So N, we kind of started out with, and Bohr had N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. And remember those energy levels, as you're getting higher in number, you're getting higher in energy, and you're getting further from the nucleus. Okay. No, we didn't talk about it. We'll be talking more about valence electrons coming up, but we did talk about periods. Okay. So we have the groups. Okay, and that's where all the similarity with their chemistry comes. But we have the periods, which goes across like this. Okay, and actually on this periodic table, I can see, for instance, francium, Fr, is in period number 7. Okay, so that means that actually, goodness, it's 87. So it has 87 protons, it has 87 electrons that we have to find homes for. 87 electrons, see how they're hanging out. And what you would see is period number 7, we would see actually that 7, I'm going to say 7s subshell. Put it up here for 87 electrons. Okay, that actually is where its valence electrons are in its period number, and is equal to 7. So we'll talk more about that. Okay. So this looks kind of redundant, maybe, hopefully. So the whole S, P, D, and F thing. S's have 1 box, 1 orbital. P's subshells have 3 boxes, 3 orbitals. A D-type subshell has 5, and an F-type subshell has 7. And I know it's coming up later, but if each orbital is 2 electrons, okay, do you buy this, that we max out at 2 electrons for an S-type? We max out, how many electrons do we max out at if it's a P-type?
8.
Not 8.
Oh, 6.
6. You had the right idea, 6. You took 3 times 2, exactly. We max out at 6 electrons there. How about D-type? It's got 5
10.
orbitals. Yep. Exactly. And how about an F-type?
14.
Yep, that's it. So that'll kind of be helpful sometimes. So in other words, and I don't know as I pick that high of a number of electrons, but francium, 87 electrons, we're actually going to find homes for those 87 electrons, but we have to follow these rules that I'm kind of talking about, and some rules that I'll talk about on Friday. Okay, cool. So what this is telling you is kind of what I have on this diagram, or on the, let's pick on principal energy level n is equal to 3. N is equal to 3, we have a 3s, 3p, and 3d. And notice within that principal energy level that actually I kind of have this mini energy thing going on here. 3s is the lowest and 3d is the highest. Okay, now finish up about shapes. So when we look, I think, did we talk about this, that if my fist is the nucleus and I have an electron out here, okay, a lot of times you'll look at figures of an atom, and instead of showing that electron, they'll say, well, the electron is bzzz here, and they'll kind of show a bunch of different dots. Okay, that's just basically to say electron can be anywhere in that region. With, I think the slide earlier said that's electron orbital with 90% probability that it's going to be there. Okay, so these actually then have shapes. These orbitals have shapes. So an S-type is, if it's an S-type orbital, it's kind of like the shape we think about. It's just a sphere. Okay. And that's what most people think, well, nucleus and electron in a cloud, electron in a cloud outside in the shape of a sphere. But if it's a P-type orbital in a P subshell, then actually it takes on what we call a dumbbell shape with the nucleus at the center. So hopefully you guys would tell me this is S-type. This looks spherical. Okay. Not just any S, but this is our 1S. And like the slide says, you can the greater the density, the more the electron has a probability of being there. So it kind of peters out on the edges. That's where Schrodinger did his work. Similar, 1s. Didn't we just do this? Oh, it's just superimposing those two. Now my videos don't seem to be working, but even though my videos aren't working, what's the difference between these two S-type orbitals?
They're small. One smaller.
One's smaller. One's closer to the nucleus. It has lower energy. So that would actually be the 1s on the left. And then on the right, it's larger and it has more energy. So that's 2s. Those are spherical. So again, orbitals are boxes. Orbitals tell the general location. Orbitals are electron clouds. Okay, they tell the general space where an electron's going to be, and they also are associated with a certain amount of energy. All right, so let's switch it up from an S to a P. So P's are dumbbell shaped. They have 2 lobes, and at the center of the lobes, where the lobes connect, is the nucleus of the atom. That is so cool. So we don't have a 1p, do we? But we have a 2p, and we have p's on up. So all right, so this is kind of getting a little picky. We can talk more about this in my other chemistry class. But we have 3 orbitals, okay? So we can call one of the orbital x, and one y, and one z. So see if you can tell the spatial difference between these 3. So this could be our p sub x, this would be a p sub y, p sub z. So if you've done much with plotting, you know we have our x, y coordinate, and actually we have a z sort of coming out of the paper. So what this is trying to show you is actually at the origin would be the nucleus, and then kind of going positive and negative for each axis, we have those lobes. Okay. So I think that's kind of cool. So that's, and these then if you guys told me you can put 6 electrons in a p-type subshell, okay? Well, if you were going to combine your p, x, py, and pz, this is kind of what they look like. That'd be where 6 electrons are. I just think that is so cool. Okay. So again, my animation isn't working, but it's kind of like we saw before. If you go up to n is equal to 3, your electron cloud's going to be further from the nucleus, and it's going to have higher energy. All right, now the D, we have to account for 5 different orbitals. So 5 regions of space around the nucleus where electron cloud can be hanging out. So here we go. 1, 2, 3, 4. Most creative, 5, the little donut orbital. So it's designated DZ2. That's my favorite. Remember, that's where, and I think it's so cool that the electron that is a 3D Z2 is hanging out in that region of space. It's amazing. Okay. So to kind of sum it up, we talked about the S-type orbitals, which are spherical. And actually, for you guys, that's kind of what I want to focus on. And the P-type, you would tell me, are, what's the shape? The P-type, yep. They're not spherical, they're dumbbell shape. Yep, that's what I was after. P-type or dumbbell shape. Okay, and the D-type, just weird. Okay. I think you guys have a homework question where you're supposed to say, maybe it's the F-type. Describe the shape of the F-type orbitals. Just do your best. Feel free to draw a sketch. But on the test, I wouldn't. So this is one of the, we said F-type subshells have 7 orbitals. This is just one of them. You're like, dude, and those little spiky things are the the shape of the electron cloud around an atom. It's amazing. Okay. Yeah, I called it Hoon's rule, but we'll get to that Friday. Pauli's exclusion principle is the whole, exclusion principle is the whole, give me a box, give me an orbital, and if I'm going to home 2 electrons in there, I have to show them one up arrow and one down arrow. Because according to this rule, they can go ahead, how does it say? Well, this has consequences, but according to this rule, remember these electrons? I put 6 electrons here for carbon, okay? According to this rule, those 6 electrons have to be unique with regard to what we call their zip code. Ultimately, they're 4 different quantum numbers. So this is to say, if I pick on these 2 electrons, they have to have different, what we say, addresses or different designations. Okay? These are both n is equal to 2. These are both in the S-type subshell, but to finally designate them, we show that one is a, actually we're going to call that a plus 1/2 spin, and this is a minus 1/2 spin. Okay, that is how we designate them. And according to Pauli's exclusion principle, you could not have a carbon atom, for instance, that had 2 with the same spin in the same orbital. Makes you want to go out and do it, doesn't it? Okay. So, this is kind of like what we talked about before. An S-type subshell has one orbital, and any single orbital can accommodate 2 electrons. So you max out at 2 in an S-type subshell. You max out at 6 electrons in a P-type subshell, 10 electrons in a D-type, and 14 electrons in an F-type. So this is kind of what I said earlier. I hope this all kind of makes sense, kind of setting you up for Friday's lecture to ultimately come up to piggyback on this whole thing. Okay. So wow, we did good. You did good. Okay. So this is due, I'm going to pull this up and show you. You're like, well, what does she expect me to know for the test? Well, things along this line. 919. Okay. So list the 4 possible subshells, and actually I went ahead and listed them there. And the maximum number of electrons that can be contained in each subshell. We did that your last slide, yeah. You're fine. The next 2 questions look like this. Sketch the 1s and the 2p. How do the 2s and 2p differ from the 1s and 1p? Differ from the 1s and 2p. Excuse me, there is no 1p. We just said that. Okay. Number 45, which electron is closer to the nucleus? That would be the lowest n, right? And then got these 2. Yeah, 44 says sketch all 5 d orbitals, n is equal to 3. Just do your best. Get the donut-shaped one coming up, right? And then if you go up an energy level from not n is equal to 3, but n is equal to 4, what would you expect those to be? Well, they would be bigger, okay, have higher energy, further from the nucleus. 46, which electron on average is farther from the nucleus? And they're both p-type, so we have 3p. How many people think 3p is farther from the nucleus? How many people think 4p is farther from the nucleus? Me too. So this assignment shouldn't be too bad. I almost feel guilty that that's all. But anyway, that's all. So we'll meet here again. Oh, nope, we'll meet tomorrow for lab. Okay?